Okay, we are going to keep working on our sequences, and we're going to come up with something called recursive formulas for them. First example, we have this sequence. And just like we were doing in the last section, come up with the next number in the sequence. So what are we doing? From 18 to 22, we added 4. 22 to 26 added 4. So it looks like our pattern is adding 4. So your next number is 34. The pattern is adding 4 to the number before the term. So the key here is you have to have the number before in order to come up with your next number. That's what a recursive formula is. It tells you the formula for a sequence based on the term before. So write this definition down. A recursive formula is a formula that relates a term in the sequence to the preceding term, the term before, or terms of the sequence. When you're working with a recursive formula, you always have to denote the first term in your formula. And remember how we do that. We either say a sub 1 equals whatever the number is, or a sub n equals whatever the number is. So going back to here, we could say a sub 1 equals 18, and then your recursive formula is a sub n equals, well, a sub n, let me make a t-chart to show you. So here's my n, here's my a sub n. Remember what that is. This is the number of the term, and this is the actual term. So the first term is 18, the second term is 22, the third term is 26, and the fourth term is 30. Okay, so to find a sub n, what we did for each one is we took the term before it and we added 4. So if you're looking for the term a sub n, the term before it, well, let's say a sub n was 4. The term before it is 3. So if I'm calling a sub n a sub 4, then this, if n equals 4, to get a 3, I have to subtract 1. So a sub n minus 1 means the term before a sub n. And then we had to add 4. So that is your recursive formula for the sequence in example 1. A sub n equals a sub n minus 1 plus 4. Whatever term you're trying to solve for, you need the term before it, and then you're going to add 4. Okay, so don't be confused by this notation. A sub n is just a term in the sequence, and a sub n minus 1 would be the term before that. Okay, example 2, consider this sequence, 4, 12, 36, 108. What is the next term? So what are we doing here? From 4 to 12, well, that's adding 8. From 12 to 36, we're adding 14. From 36 to 108, we're adding 72. I don't see a pattern in that. So what else could we be doing to get from one number to the next? So instead of trying to add a number, we could look at multiplying by a number each time. So to get to 12, we'd have to multiply by 3. From 12 to 36, so look at that, multiply by 3. And from 36 to 108, multiply by 3. So we have a nice pattern here, very easy to figure out. You're multiplying by 3 every time. So if you do 108 times 3, you'll get your next term, which is 324. Okay, what's the recursive formula for the sequence? So you're always going to start with a sub n equals the term before it, a sub n minus 1, and then what are you doing to find each one? Well, here we're multiplying by 3. You could also flip the order on that. You could say it's 3 times a to the n, a sub n minus 1. But those are the exact same thing. It doesn't matter which order you do it. I kind of like this one because it's easy to think, okay, I always have to start with the term before it, and then what do I do? Graph the terms of the sequence as an ordered pair. So n, of course, is the number of the term, and g sub n is going to be the actual term number. So my first term is 4, so 1, 4. My second term is 12, 2, 12. My third term is 36, so 3, 36. My fourth term is 108, 4, 108. My fifth term is 324. That's not going to fit on my graph. What kind of graph does it form? Your first thought should be linear. Is it a straight line? Definitely not. Is it a curve? Absolutely. It is a curve. What kind of curve is it? Well, remember, this is kind of what we did the preview of yesterday, or well, in the last section. It's either potentially, you might know if it's an exponential curve or a quadratic curve. A quadratic curve is going to have small increases in your rates of change. So in other words, your slope isn't going to increase. It's going to be different between each point, but it's not going to be huge, huge jumps. This one, you're getting huge jumps. And imagine if you were able to graph the next one, you'd be way off my computer screen. So that's telling you it's an exponential form. So what kind of graph does it form? It forms an exponential curve that starts low and continues to get high quickly. There you go. Okay, there are different types of sequences. As you just saw, we did one, our first example, we had one where we were adding the same number each time. And example 2, we were multiplying by the same number each time. Those are your two different types. The first one is an arithmetic. Yes, I know you think that word's arithmetic, and it is if it is a noun, but here we're using it as a description of sequence, which makes it an adjective. So as an adjective, you pronounce it arithmetic. An arithmetic sequence is a sequence where each term is the result of adding a previous term and a real number. When you have an arithmetic sequence, you will get a linear relationship. Because you are adding a constant number each time, your slope will remain constant. Therefore, you'll have a line, a straight line. If it's a geometric sequence, then it's a sequence where each term is the result of multiplying a previous term and a real number. So when you're multiplying, that's going to make your slope different. You're going to start increasing more rapidly, and that makes an exponential relationship. So geometric sequences are going to be exponential relationships. So knowing those definitions, of course, pause them and write them down. But then knowing those definitions, which type of sequence is example 1 and what's example 2? Example 1, you are adding each time, and that makes it arithmetic. Example 2, you are multiplying to get each term, so that makes it geometric. Okay, you need to know the difference between those two. You can also know based on whether you're getting a linear relationship or an exponential. Example 3, consider this sequence. What are the next 3 terms? So first, I always try to add. Can I add something to get each term? Well, from 20 to 33, I'm adding 13. From 33 to 46, I'm adding 13. And from 46 to 59, I'm adding 13. So what are the next 3 terms? Well, take 59, add 13, you get 72. Take 72 and add 13, you get 85. And add 13 one more time, we get 98. The recursive formula. So a sub n. So any term you are looking for, you have to take the term before it and do what? Add 13. There's your recursive formula. Again, don't get tripped up on the notation. Oops, except for I did it wrong. Let's fix that. The term before it is n minus 1, not n plus 1. Is this sequence geometric or arithmetic, and why? You're adding the same number each time, so that makes it arithmetic. And let's make it a nice, neat sentence. So let's say the sequence is arithmetic because we are adding a constant each time. Okay, describe what the graph will look like using complete sentences. So I don't even have to graph this because I know if I have an arithmetic sequence that I'm going to have a linear relationship. And I know a linear relationship means I'm going to have a straight line. The graph will be a line with a constant slope. There you go. What's the slope going to be? You want to be really good, really specific. The constant slope.